Okay, so the next part of differentiation is actually putting it into a context. And I'm going to use basically to start with the context that I initially described it in. So the proof that I used at the start was basically showing how it makes gradient or finding the gradient of a specific point or of a function easier. Okay, so now we're actually going to use it to do that. Okay, so if you want, go back and have a look at those first few slides from the first PowerPoint that I put up. And it might help you with this a little bit. But the idea, obviously, if we differentiate, it's used in lots of different situations, but the main three are to find the gradient of a tangent to a curve, right? That sounds pointless at the moment, but it's quite useful in what we're going to do soon. Okay, so that's what we're building up to. We can find the gradient of a curve. Okay, so it will be at a specific point because obviously the gradient of a curve changes. But it's the same idea as a gradient of a tangent to a curve. And then the rate of change. Rate of change is very, very important. As I say, that's how we look at the rate of change of a population. It's used quite a lot in terms of speed, acceleration, and things like that. So it's a very, very important process, and this is the context we used it in. Okay, basically the additional step now is exactly the same as what we've been doing for the last few lessons, but now you're going to be given a value to substitute in after you've differentiated. So as I've been going through this, I've been saying you want it in its simplest form so that you can use it. This is where you're going to use it. So you're going to be given an x value and you're going to be finding the value at that specific point. Okay, so the idea, just as a recap, the idea of differentiating is it allows us to find the rate of change at a specific point within that function. Okay, so what that means for the graph is that if we differentiate the equation of the graph, okay, we can find the rate of change at any point along that graph. So obviously the rate of change changes throughout that graph. Okay, so we can find the specific rate of change at any point when we substitute an x value. What that means for the graph, at least, is that we'd find the gradient of the curve or the gradient of the tangent to the curve at that specific point. Okay. Right, so an example just quickly. So a parabola has equation y equals x squared minus 5x plus 6. A tangent to the curve is drawn at the point P, which is 4, 2, and we're going to find the gradient of this tangent. Okay, so you won't always be given a diagram, but here's a snazzy one that I drew for you. Okay, and we're going to find the gradient of a tangent at a specific point. So that's a tangent there. So remember, it just touches the curve at one point only, and that is the point in this case 4, 2. Okay, we're going to find the gradient of this tangent. So straight away, we're dealing with gradients. What a lot of people try and do is they try and go back to what they've done in terms of gradient before. But we couldn't do anything in that respect here because we don't know 2 points, we only know 1 point. And because it's a tangent, we can only find 1 point because the only equation we've got is the curve. And you don't know anything about kind of perpendicular gradients, you don't know anything about angles, they're mixed with x-axes and stuff. So this is just another string to our bow. So the problem with that is, again, you've got to kind of select the appropriate method from an ever lengthening list. So now when you ask for gradient, you've got another thing that you can do. So you have to know which one it is. So with the 3 things we've already done in terms of gradient, you've now got a 4th. Okay. All right. Yeah, that's what I just said. Yeah, that's what I just said. But that's what we're going to do. Okay, so we can differentiate this curve. And what it would allow us to do, given any point on there, we could find the specific gradient of the tangent at any point on there. But we're looking at this point specifically. Okay, so the first thing we want to do is differentiate. So obviously, before we differentiate, we want to check that it's in the best form. We want to check it's in differentiable form, which this is. If it's not, we might have to do some jiggly-pokery, but this one's fine. Okay, so we can just go ahead and differentiate. So we would write dy by dx equals. Right, first bit differentiated is just 2x, second bit differentiated is just 5. The final bit disappears, the constant differentiates to 0. Okay, so now this is the derivative. Okay, and this is, in the past few examples, this is where we've left it. But now we're going to use this. We're going to use this. It's going to allow us to find the rate of change at a specific point, in which case, in this example, it's the gradient. Okay, so gradient is just rate of change. So because we've got a point 4, 2, okay, and obviously our equation is in terms of x, we just want the x value. Okay, so we want the fact that it's when x is 4. Okay, so when x is 4, the dy by dx, which is the rate of change, will equal 2 times by 4. Okay, so just substituting the x for the 4, and then take away 5. 2 4s are 8, minus 5 is just 3. Okay, and that's it. At P4, at the point P, 4, 2, the gradient of the tangent is 3. Okay, that's literally it. But you can see where this is going to go from here. okay? Obviously, when we're dealing with straight lines, we often want the full equation. So we could then go on and actually find a full equation. We're just going to kind of ease you in a little bit here. Once we found the gradient, the fact that we've already got a 0.42, we could find the equation quite straightforward, okay? But we're just leaving it there. All we wanted to find was the gradient. But you could be asked this exact same question with different wording. It could be, what is the rate of change at the 0.42? It's still just 3, okay? So there's lots of different ways you could be asked this question. But when we're dealing with rate of change, when we're dealing with gradient, it's the same thing. In other words, we need to differentiate. So this is a slightly different one now. So we're going to find the gradient of a tangent to the curve y equals 6 over root x at the point where x equals 9. Okay, so this is our function here, and the problem this time is that it's not in differentiable form, so we need to change it into differentiable form. So the root x becomes x to the power of a half, in which case when we move it to the top, it becomes minus a half. So 6x to the power of minus a half. My computer's having a meltdown. There you go. 6x to the power of minus a half. Okay, so that's in differentiable form. We've not differentiated, so I've not said dy by dx, which is y equals 6x minus a half. These two things are the same, but next, in order to find the gradient, I am going to differentiate. So next I would write dy by dx and just go through with my whole differentiation. So minus a half times by 6 is minus 3x to the power of minus 3 over 2. Sorry, I had to just run for the doorbell there. So it paused for me, but I don't think it paused for you. So I'll just continue as if nothing happened. Right, dy by dx equals that. Minus a half times by 6 is minus 3. Drop it by 1 is minus 3 over 2. So this is our derivative. Our derivative allows us to find the gradient at a specific point. The point that we want is x equals 9. So we want to substitute x equal to 9 into this. Right, but the problem is, what is 9 to the power of minus 3 over 2? So it's easier to change this back into kind of the original form and write what minus or something to the power of minus 3 over 2 means. Okay, so we want to first of all change this. It's going to work. So x to the power of minus 3 over 2 is 1 over the square root of x cubed. Okay, times by minus 3 is minus 3 over the square root of x cubed. Take as much time as you need to get to that point. If you need more lines of work in, then do it. Okay, this is what you need, and now we're trying to find the gradient at this point x equals 9, so we're going to substitute x equal to 9 into this. It seems complicated, okay, but this would more often come up in a non-calculator test, so we can pop it in to our derivative, so it's minus 3 over the square root of 9 cubed. Do the square root bit first, it's much easier. It doesn't make any difference. You can do the 9 cubed first if you want to, but it's just dealing with bigger numbers. So square root of 9 is 3. 3 cubed is 27, nothing's changed along the top, but then minus 3 over 27 simplifies to minus a ninth, okay? And that's it, okay? We found the gradient to the curve y equals 6 over root x at the point where x equals 9, that's it. But as I say, you could go on and you could have to find the actual equation, or there's more to come, but that's generally what you do next, okay? Right, so yeah. The curve has equation y equals 3x squared minus 12x plus 6. Find the x coordinate at which the tangent to the curve has gradient 6. So now what's happening is we're told the answer. So in the previous ones, we've been looking for the gradient, given the x coordinate. Now we're given the gradient, and we're going to try and find the x coordinate. So there's going to be a slight change here in terms of what we do. Basically, what's going to happen is rather than substituting in an x, we're going to make our derivative equal to the gradient, okay, and then work back from there. Either way, we have to differentiate. So check if it's in differentiable form. It is, so just go ahead and differentiate, in which case we write dy by dx equals, and in this case it's 6x minus 12. Okay, 6 just disappears. It's fine like that. Okay, so we're going to find the x coordinate at which the tangent to the curve has gradient 6. So this is not a case of substituting in 6. If it said find the gradient when the x coordinate equals 6, then we'd substitute in 6. But this is the opposite. We're going to find when basically the gradient equals 6. So in other words, when 6x minus 12 equals 6. Okay, so there is a point at which dy by dx equals 6. In other words, when 6x minus 12 equals 6. Now we've given ourselves an equation, and obviously we can solve it. We can solve it for x, which is our x coordinate when the curve has a gradient 6. Okay, add 12 to both sides, divide by 6. The gradient of the curve is equal to 6 at the point where x equals 3. Okay, so read the question carefully, because obviously this one is slightly different, involves a slightly different process at the end. But the bottom line is, it's still differentiation. Okay, and even though it says any stuff about gradients, and we've obviously dealt with gradients before, We've got to think about the information that we've got and what we can get from that information. Okay, we can't do anything in terms of gradients with the equation. Apart from anything else, this is an equation of a curve. And we don't really have any methods yet, apart from now differentiation, where we can deal with or find the gradient of a curve. Okay, more often than not, these are going to be curves, so that's going to be a clue in itself. Okay, but again, you don't have any points here, you don't have any angles, you don't have anything like that, you don't have perpendicular lines, so you have to go down the route of differentiation now. Okay.